we will discuss two main concepts, exponential expressions and polynomials. In Module 5, Section 1, our main focus will be exponents. Remember that exponents that are natural numbers or positive counting numbers are shorthand notation for repeating factors. In this example where we have 3 to the 4th power, 3 is the base and 4 is the exponent. The base is the repeated factor, and the exponent indicates how many times we should repeat the factor. Let's try to evaluate a few exponential expressions. So as we just saw, 3 to the 4th power can be rewritten as 3 times 3 times 3 times 3. And then using pen and paper or a calculator, we can evaluate this at 81. In the next example, we have negative 5 to the 2nd power. It's important to note that because negative 5 is in parentheses, that entire factor is being repeated. So we can rewrite this as negative 5 times negative 5. That will equal a positive 25. For those of you that are trying to use scientific or graphing calculators, if you did not put parentheses around the negative 5, it would not give you the same answer. Let's notice how C is different than B. Again, we have a negative number raised to a 2nd power, but the negative 6 is not contained in parentheses. That changes the entire problem because in this case, the 6 is the only number attached to the exponent. So we could rewrite it like this, negative 1 times 6 squared. And in this example, the negative will not be a repeated factor. So we continue to expand and we have negative 1 times 6, or negative 36. Make sure you're careful to recognize when you do have parentheses with a negative base, when you do not have parentheses, where you will not have a negative base. Instead, you will have a negative 1 times an expression. In the next example, let's simplify inside parentheses first. 2 times 4 is 8, so that gives us 8 cubed. Remember that 8 cubed can be rewritten as 8 times 8 times 8. And this will simplify to 512. In the 5th example, 3 times 4 squared, again, this 4 squared, 4 is the only number being taken to the 2nd power. The 3 does not raise to the 2nd power. So we can rewrite this as 3 times 4 times 4. And again, using hand or using a calculator, we can evaluate this to be 48. And in the last example, 1/3 to the 3rd power. 1/3 is our base, so we are repeating multiplication on the fraction. Remember, when we multiply fractions, we multiply all of the numerators, which will give us 1, and all of the denominators, which would give us 27. Now that we've reviewed simplifying exponential expressions, let's evaluate some algebraic expressions that contain exponents when we are given a value for x. First, let's find 3x squared when x equals 5. So we replace x with 5. And remember, 5 here is the only number taken to the 2nd power. So the 3 should not be a repeated factor. This will become 3 times 5 times 5, which will simplify to 75. In the next example, find negative 2x squared when x equals negative 1. So we replace x with negative 1. And similar to the example on the last page, the entire expression or term negative 1 is being taken to the 2nd power. So that negative sign will be repeated. This can be rewritten as negative 2 times negative 1 times negative 1, which will reduce to negative 2. many exponent rules that we learn in this section. This is called the product rule for exponents. If m and n are positive integers and a is a real number, then we can say a to the m power times a to the n power can simplify to a to the m plus n. Basically, if we have the same base that we're multiplying together, we would add the exponents. So let's look at a few examples. In part A, I'll show you why this is true. We know that 3 squared could be rewritten as 3 times 3. The second 3 squared could be rewritten as 3 times 3. And if we wanted to simplify this or write just an exponential expression, we have 3 repeated 4 times. That's the same thing as adding the original 2 and 2 that we saw were exponents. So 3 squared times 3 squared is 3 to the 4th. And when evaluated, this will become 81. In the next 3 examples, let's simply use the product rule that was given. So we have x cubed times x squared. It's important to recognize that x and x, the base has to be the same. Here the bases are the same, so we write the base one time. We add the exponents. So it becomes x raised to the 3 plus 2, or x to the 5th power. In the third example, z cubed times z squared times z to the 5th. The base is z each time, so we can write z once and add all of the exponents. And this will reduce to z to the 10th power. Example, 3y squared times negative 4y to the 4th. We can rearrange our terms so that we put our constants next to one another and our variables next to one another. 3 times negative 4 times y squared times y to the 6th. Excuse me, times y to the 4th. We multiply 3 times negative 4, which becomes negative 12. Using our product rule, y squared times y to the 4th is y to the 6th. When we're multiplying identical bases, we add the exponents. We do not multiply or add the bases. That if no exponent is written, it is assumed to be 1. For example, 9 is the same thing as 9 to the 1st. X is the same thing as x to the 1st, and so on. Here's the second exponent rule, the power rule. If m and n are positive integers and a is a real number, then a to the m, all raised to the n power, would be the same thing as a raised to the m times n. Essentially, if you have one base and multiple exponents, you will multiply. Let's try a couple of examples. First, we have 2 cubed raised to the 3rd power. So using this rule, this would become 2 cubed times 3. So we multiply those 3's together in the exponent, and that will give us 2 to the 9th power. Now, typically, we don't want to leave a number raised to a power because we can simplify that. And once you multiply 2 times itself 9 times, that will become 512. In the next example, we have x to the 4th raised to the 2nd power. So because we have multiple exponents, we will multiply those exponents. And the result is x to the 8th power. It's really an extension of the first two that we've seen, and it's called the power of a product rule. If n is a positive integer, and a and b are real numbers, then if we have the product of a and b all raised to the n power, that's equivalent to raising each factor to the n power. Our example, 5x squared y, all raised to the 3rd power. We can rewrite this. We have 3 different factors, 5, x squared, and y. So we can rewrite this as the product of each factor raised to the third power. That will give us 5 cubed times x squared cubed times y cubed. Now this isn't a good form to leave it in. We have a number raised to a power. We have one base with multiple exponents, so we can continue to simplify. And when we do, 5 cubed becomes 125. With the x squared raised to the third power, we have one base with multiple powers, so we multiply those powers together. We bring down the y cubed. So this simplifies to 125 x to the 6th y cubed. Let's try a few more examples using the power of a product rule. Here we have -5 x cubed y squared z to the 4th, all raised to the second power. Remember, we can take that exponent and apply it to each factor individually. And if we do, it looks like this. I'm going to keep my -5 in parentheses. If I don't, then we will lose a negative somewhere, and our sign and the answer will differ from the correct answer. So we have -5 squared, x cubed squared, y squared squared, and z to the 4th squared. As we continue to simplify, -5 squared, or -5 times -5, is 25. X cubed squared, here we have multiple exponents on one base, so we multiply. 3 times 2 is 6. Again, y squared to the second power, multiple exponents on one base, so we multiply. Y to the 4th power. And lastly, we have one base in z with multiple exponents, so again, we multiply. And this would be the simplified product. 25 x to the 6th, y to the 4th, z to the 8th. Example, -xy to the 4th, all raised to the 6th power. First, I'm going to rewrite it like this. Remember, a negative coefficient is the same thing as -1. So -1 times x times y to the 4th, all raised to the 6th power. And now we can rewrite this expression where each factor is raised to the 6th power. We have -1 to the 6th power times x to the 6th power times y to the 4th raised to the 6th power. Now once you evaluate this number, -1 to the 6th power, or -1 times itself 6 times, that will become a +1. X to the 6th won't change. Y to the 4th raised to the 6th power, we have one base with multiple exponents, so we multiply. And that becomes y to the 24th. We can rewrite this as x to the 6th, y to the 24th. Exponent rule, this is the power of a quotient rule. And it's very similar to power of a product. If n is a positive integer and a and c are real numbers, then if we have a fraction or a quotient instead of a product, we can write the numerator raised to the power as well as the denominator raised to the power instead of the entire fraction raised to 1 power. So let's try that in this next example. We have p over 4, all raised to the 4th power. We can rewrite this as the numerator raised to the 4th power over the denominator raised to the 4th power. P to the 4th won't change, but remember, anytime we have a number raised to a power, we want to simplify that. 4 to the 4th power will become 256. And there's no more simplification that can be done. Example that contains the power of a quotient rule. Here we have 2x to the 4th over 3y to the 5th, all being raised to the 4th power. So we start using our power of a quotient rule, which says we can rewrite this as the numerator raised to the exponent over the denominator raised to the exponent. Once we do that, we can use the power of a product rule in both numerator and denominator. And this would become 2 to the 4th power, x to the 4th raised to the 4th power, all over 3 to the 4th power, y to the 5th to the 4th power. And as we continue to simplify, 2 to the 4th power is 16. X to the fourth power raised to the fourth power. We have one base with multiple exponents, so we multiply those exponents. So we have 16x to the 16th over 3 to the fourth power is 81. With the base of y, we have multiple exponents, so we multiply. That becomes y to the 20th power. 16 and 81 share no common factors, so this fraction is simplified. Exponent rule, and this is the quotient rule for exponents. Remember the product rule when we were multiplying the same base, we added the exponents. Essentially here, if we are dividing the same base, we subtract the exponents. And I'll show you a shortcut after we go through a couple of examples. So starting with this example, x to the 7th over x cubed, we write x one time, take the numerator exponent, 7, minus the denominator exponent, 3. And this would simplify to x to the 4th. Another way to think of this, x to the 7th is 7 factors of x. Now this is not the shortcut, but this is just another way to visualize what's happening. So we could write out all 7 factors of x over 3 factors of x. And remember, when we have common factors in numerator and denominator, they cancel. So we would have 3 factors of x cancel in numerator and denominator. And we would be left with 4 factors of x in the numerator. X times x times x times x is x to the 4th. And so that's just another way to visualize what's actually happening when we use the quotient rule. Quotient rule in this example, to simplify the expression, 9a to the 4th, b to the 7th, all over 3ab squared. Anytime we have coefficients, we want to simplify those. 3 divides 3 once, 3 divides 9 3 times. So we can reduce this to 3a to the 4th, b to the 7th, over 1, and we don't have to write the 1, so ab squared. Now remember, the a in the denominator, because there is not an exponent written, that exponent is understood to be 1. Now using the quotient rule, we write 3, you can write a once, and take the numerator exponent minus the denominator exponent. We write b one time as well, numerator exponent minus denominator exponent. As we continue to simplify, this becomes 3a to the 3rd, b to the 5th. Exponent rule is the zero exponent property, and that states that any real number other than 0 raised to the 0 power has a quantity of 1. Okay, this is something that can be shown with the quotient rule that we defined before, but just remember that any quantity raised to the 0 power becomes 1. Don't confuse this though. Remember, if an exponent is not written, that is not the same thing as an exponent to the 0 power. Okay, that is not true whatsoever. If an exponent is not written, it has an understood 1 as the exponent. So let's try a few examples. We have 5 to the 0 power, and remember, any real number other than 0 raised to the 0 power is 1. So 5 to the 0 power is simply 1. The same can be said about b. We have x, y, z cubed, all raised to the 0 power. If we wanted to use the product rule, then we could see that this would become x to the 0, y to the 0, z cubed to the 0, in which case every base raised to the 0 power would become 1. So we'd have 1 times 1 times 1, or just 1. Now c might be a little bit tricky. We have negative x to the 0 power, and remember, if the negative is not inside parentheses, it is not being raised to the exponent. So we would rewrite this as negative 1 times x to the 0 power, which would be the same as negative 1 times 1, or negative 1. Another expression using most of the product rules, most of the exponent rules that we've learned in this section. So we start in the numerator. We have the power of a product. So we can rewrite this as each factor raised to the exponent. It becomes 2 cubed, a cubed to the third power, b to the fourth to the third power, all over a denominator that's not going to change. As we continue to simplify, and we'll deal mostly with the numerator first, 2 to the third power is 8. A has multiple exponents, so we multiply, that's a to the 9th. B has multiple exponents, that becomes b to the 12th because we multiply again. Again, so far we haven't done anything with the denominator because so far there hasn't been anything that needs to be done. Now at this point we can start simplifying our numerical coefficients and also using our quotient rule to combine exponents. We have 8 divided by negative 8, and 8 divided by negative 8 becomes negative 1. So we have negative 1. We write a one time, the exponent on top minus the exponent in the denominator, 9 minus 9. Do the same thing with b. We write b raised to the 12 minus 2. As we continue to simplify, we have negative 1, a to the 0 power, b to the 10th, which is negative 1 times b to the 10th, or just negative b to the 10th. Make sure you work lots of problems so you can have practice at using all of these different exponent rules. And in the next section, we will introduce a few more.